So let's get started. Before we dwell into the journey of containers, it's very important to understand how this entire ecosystem have evolved. So if we take ourselves 20, 25 years back, there was only one thing in the industry, and that thing was data centers. So you have a place, you have servers, network devices, load balancers, firewalls, and so many other equipments. So we completely create that data center so that we can host our applications on top of it. And that typical model was known as one application per server. That was the time when we were having mainframes, Unix based operating systems like Solaris, AIX, or HPUX, which was used by almost every organization. But the problem was one application per server, which means you need to put a lot of cost in the infrastructure. And on top of that, if you are hosting one database on one server, you cannot host another database of different version or different flavor on the same server, which means you have a very poor resource utilization in terms of memory, CPU, network cards, and so on and so forth. Then you used to have dedicated infrastructure teams. For network team, different set of people. For operating system, again for Windows and for Unix, different teams. So the team size was huge. And on top of that, one of the biggest problem was downtime. If there is an error in the application or database or operating system or a hardware failure, your entire application is down. So you used to have huge long downtimes. And today we cannot afford to have downtimes. But till 2010, this was how we used to run our applications. Then there was a change. And that change have been introduced by a technology called virtualization. So virtualization came. A small idea. Why can't we create a pool of servers and install one lightweight software on top of that? That lightweight software is called hypervisors. So when we talk about hypervisors, what they do, they create a pool of servers and then they club that. And then you can use that pool and you can create virtual machines on top of it. So virtual machine is nothing. It is virtual hardware plus operating system. As Linux was evolving from 2010 onwards and customers were looking to migrate their old legacy operating systems to Linux, and this is how the hypervisors became the changer for the entire industry. Now you can have three servers and you can install 15 or 16 virtual machines on top of it. And that have changed the entire ecosystem in the industry. Now this was known as multiple applications on one server. So you have a physical server, you can create different virtual machines, and on top of those virtual machines, you can host your applications. Many advantages were provided by virtualization. Number one, you can start small. You can start with a VM which is having 2 GB of memory and 2 core CPUs. As your application is scaling, you can increase the resources on the fly. You need not to have any downtime. You can increase memory, you can increase CPUs, you can increase network cards, you can even increase the disk size now. Now, in the modern hypervisors, you can even increase the root disk size. You start with 20 GB and you can increase it to 30 GB or 40 GB without downtime. So the utilization of resources were better with hypervisors. Downtime was less. And you can create server on the fly. Now, example, in the past, if you want to create one server, you need to have a hardware, you need to have multiple teams around there. So one server used to take approximately 1 month to come up and running. Now that is reduced when we talk about hypervisors. You raise a ticket with your virtualization team, and within 5 to 10 minutes, you will be having your server up and running. And your development or your application ecosystem starts then and there. But this was also having certain limitations. Now, on one VM, can I run two different applications or similar applications with different versions? No, you can't. Then the people started thinking about it. Can't we do something wherein we can have virtualization at OS level as well? This is where containers came into picture. Now, when we talk about containers, we need to understand two terms as well. One is called namespaces and one is called C groups, which I will explain in next 5 minutes. But from hypervisors, we moved to something called container runtime interfaces. You can take one server. It can be a physical server or it can be a VM. On top of that, you need to just install one software. And that software is called CRI, Container Runtime Interface. Now, there are various CRIs available in the industry. You can have Docker, you can have Podman, you can have Cryo, you can have Containerd, you can have Kata containers, gvisors. So there are many CRI tools available in the industry. You install that, and then what happens? You can install multiple lightweight operating systems or applications on top of a single server. And those lightweight applications, those lightweight operating systems, they are called containers. And the good part is they all work in isolation. They are immutable. When we talk about running a container, it's having everything bundled in it. Your application code, your dependencies, your operating system, your vulnerability fixes, everything is fixed in one bundle. And that bundle, when it unpacks, it is your container. So you get everything all together. And you need not to worry either you are running it on Ubuntu or you are running it on Rocky Linux or RHEL. You need not to worry because that is entirely taken care by your CRIs. And the good part is that's the thing which comes in the industry, and that's called build anywhere, run anywhere. You can build your container images or containers on your laptop and you can run it on any production environment. You can go to AWS, Azure, GCP, anywhere, and you are going to see the same thing is working as it is on any platform. And this is how the culture of DevOps have also been evolved. So your development teams and your operations team are working together. Development teams are focusing on building applications, and your operations team are focusing on deploying applications and managing them. So containers have brought your 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 development teams as well as your operations team together, right? Next. Now, before we jump into what is Docker, I would like to showcase something. So I'll switch back and I'll try to explain it here. So whenever I talk about Docker or containers, I usually come across one question: how old containers are. Now, to be very honest, they are very old. In fact, in the legacy Linux or Unix based operating systems, there was something called containers, but they were legacy containers. The modern containers started from 2008 with the concept of zones. This was the concept which was introduced by a company called Solaris, Sun Microsystems. So Sun Microsystems, with their Solaris based operating system, they came up with one concept called isolation, and that isolation is achieved using something called zones. So you create one OS, and on top of that OS you create something called zones, and those zones were in entire isolation. So you can run one application in one zone, another application in another zone, and so on and so forth. But this was just for Solaris, a Unix based operating system. And when Linux came, Unix started to die. And that is where in 2008, another concept came in the industry. And that concept was called LXC. LXC means Linux containers. Now, how Linux container evolved? Thanks to Google. Google contributed two major concepts in the Linux kernel. One was namespaces, and another was C groups or control groups. Now, what is namespaces? You need to explore the Linux namespaces after this webinar because it will give you a lot of understanding of containerization. But what namespaces are? Namespaces provides us something called isolation. Process namespace will give a process isolation. Network namespace will give us network isolation. Mount namespace will give us file system isolation, and so on and so forth. So what happens? There are multiple namespaces which works together. So these namespaces will going to provide us isolation. And then comes control group. Control group will going to provide us something called quotas. So I want one isolation to be created and it should have certain quotas associated with it. So quotas will be provided by C groups, memory, CPU, and the isolation will be provided by namespaces. You combine namespaces and C groups, you are going to get something called containers. So these two concepts were introduced in the Linux kernel by Google, which gave a birth to a term called LXC, Linux containers. But it was too complicated at that point in time. And Linux was also new. And hence, that's the reason we didn't see much about LXCs. Then in 2010, 2009, another concept came in the industry called LXD. LXD stands for Ubuntu containers. So Ubuntu or Canonical, they also tried to give something to the industry in the form of containers. But again, at that point in time, it didn't become very popular. During this time, there was a company called Cloud. A French-based company. What they did, they took this concept LXC and they created one PaaS platform, platform as a service. And their customers used to come here and deploy their applications. When the customers were deploying the applications were getting deployed in the form of containers. So it was container as a service which they were offering. But this company was not doing good. And hence that's the reason in 2012, they thought of closing it off. Then their management decided, instead of closing it off, let's do one thing. Let's make the projects with whatever projects we have used in our PaaS platform, let's make them open source. So they released multiple open source projects. And one of those projects was Mobi project. And this Mobi project have got a lot of attention from the industry. And then this Mobi was known as Docker. So the Docker is actually a Mobi project. The original name of Docker is Mobi. Till date, if you go to the repositories, you will see it with a name called Mobi project. So in 2013, Mr. Simon Heikis, what he did, he created Docker Inc., a San Francisco-based organization. And since then, containers started getting the traction and popularity. Even in 2016, Docker released two of their offerings. One is called Docker CE and one is called Docker EE. CE stands for Community Edition and EE stands for Enterprise Edition. So there was something called Docker Enterprise Edition in the past. This happened in 2016. But again, a change came. In 2019, Docker again just became Docker CE, only open source. Docker EE was acquired by a company called Mirantis. Now they sell it as MKE, Mirantis Kubernetes Engine. So MK is nothing Docker Enterprise Edition in the past. So since 2019, now Docker is entirely open source. This is how Docker have evolved in the past. So it all started from LXC and now whatever we see is actually endless. There are many things in container ecosystem which is going on. This is how Docker came into the existence. And containers started getting the traction from 2013 onwards. And today we are sitting at 2025. You go to any organization, they are having containerization in their roadmap. They want to do more and more containerization. They want to build more and more applications using microservice-based architectures, right? This is how Docker came. Now let's switch back and understand what Docker is. So when we talk about Docker, we just need to remember three things: build, ship, and run. So Docker is a platform to build, ship, and run your containerized applications. What is build? You need something to run. That something is called image. How we create images? We create images using Docker files. So we write simple instructions as per our requirements. And what we do is we ask tool to create image for that. So we just need image. So image creation in Docker is known as build. So we build our applications. Once our applications are built, what we do? We don't want to keep them with us in our laptops. What we want to do? We want our entire organization, or at least the technology team, should use that. So what we do? We put that in the centralized location. So putting your images at centralized location is called shipping. We are sharing our images. This is where a concept of registry will come into a picture. We will explore registries in some time. So we build images, we share images. Sharing images is called ship. Now your developers and your infra, your ops team, they are having the access to the registries, to the shared library. What they do? They download the image and they run them as containers. So they just pull the image, execute a command, and that command will going to unpack your image and you will see your application is up and running. So in a nutshell, when we talk about Docker, we just need to remember three things: build, ship, and run. And hence we say Docker is a platform to build, ship, and run your containerized applications. Build means building images, ship means sharing images, run means running containers. Build, ship, and run, all done. Now, before we dwell into the other intricacies, let's understand the architecture of Docker first. So let me explain it on a board first so that we can understand it clearly. Now, when we talk about Docker, Docker is actually a client server based architecture. So we are having a client and we are having a server. This client is nothing. This is called CLI, command line interface. This is where most of the users will going to interact or play around. There is only one command in Docker, and that command is called Docker. So users will going to play around with Docker command, which is client. And this server is nothing. This is Docker daemon, the core component of Docker. Example, let's say this user wants to create a container. He will just going to run Docker container run -itd -name -net and then the name of the image. As soon as he enter, what will happen? Docker will going to convert that command into REST API call. And that REST API call is handled by Docker daemon. Docker daemon is responsible for the life cycle of every object in Docker. Images, network, volume, containers. The entire life cycle of objects will be taken care by Docker daemon. Once it is done, what it will do? It will actually pass the control to another component. That component is called containerd. Containerd is specifically, it's a high level container runtime. This is responsible for the life cycle of container. Pulling images, pushing images, then creating container out of it, identifying the network or storage for a container. The entire life cycle of a container is taken care by containerd. And then what containerd does? Containerd pass the control to another low level runtime. That low level runtime is called runc. Runc is responsible for implementing the guidelines for container creation, which are created by OCI. OCI stands for Open Container Initiative. You cannot create anything and sell. No, there are rules. Those rules are created by OCI. So there are 3 rules which OCI have created, and even you can go through those rules. So if you go to opencontainers.org, you should be able to see the complete details. Open Container Initiative. In 2015, this was established to create the governance, to create the specifications for container ecosystem. So there are 3 specifications: how the containers should run, how the images should build, and how the distribution of images should be done. So runtime spec, image spec, and distribution spec. These 3 specifications has been created by Open Container Initiatives. There were 2 actually, runtime and image spec. This third one have been introduced lately. Now, this runtime specification, how a container should run in your OS, is actually being done by this runc. Then runc will pass those details to your Linux kernel. So this is your kernel. Then your kernel will going to implement everything with the help of namespaces and C groups. And then a lightweight isolated environment will be created, and this lightweight environment is called container. So from user perspective, we are just running a command. But from Docker perspective, that is getting converted into APIs. The APIs are managed by Docker daemon. Docker daemon will pass the control to containerd. Containerd is responsible for the life cycle of your container, being acting as a high level container runtime. Then it will pass that information to a low level runtime, which is runc. Runc is responsible for implementing OCI compliances or specifications. Then runc will pass that information to a kernel. Kernel will implement the logic with the help of namespaces and C groups. And then finally, we are going to get our container up and running. All done. And if you belongs to a core Linux, you can see all these things in the processes, in the Linux namespaces. This is how the entire architecture of Docker works. Let me go through the slides and just show you. Docker engine architecture. So if anyone is saying Docker or Docker engine, it's the same thing. So you have a CLI, Docker, where you are installing a Docker, that machine is called Docker host, daemon, then containerd, then runc, and then finally you are having your kernel. And then you are getting containers. So you can create 1 container, 2 container, 3 container, unless and until you are having resources available in your Docker host, you can create n number of containers. Now, another thing, sorry, which is important, that is objects. Now there are 4 objects in Docker: images, containers, networks, and volumes. Now, to understand this, I think I can give you a simple example. Now, let's say we have purchased a laptop. Now, purchasing a laptop doesn't mean it will going to work for us. No. What we need to do in order to get our laptop in a working condition, we need to install something. And to install something, we need something. And that something is called your Windows OS or your Linux OS or your Mac OS. So you need operating system. And how operating system will come? It can be a DVD, it can be a CD, it can be in a pen drive, it can be in a flash drive, but you need something to start your laptop. Similarly, when you talk about containerization, in order to create container, you need something. That something is called image. Image can be only operating system. Image can be your security vulnerability images, means the images which can run the scans. You can have various application images. Example, your Nginx, your Tomcat, your databases, your Apache or whatsoever. So you need something. Something is called image. Image is a read-only template. In containerization, if you want to do anything, either you need to create your image or you need to update your image. Unlike normal operating systems, we log in and we troubleshoot. In containers, we don't troubleshoot because they are immutable in nature. What we do, if there is a bug, if there are any configurations which you want to change, you're not going to log in into a container to do the things. No. What we do, we update our image. Version 1, version 2, version 3. And what we do is we roll out that image. We don't want humans to log in into a container and then start doing a troubleshooting. Not at all. That is all taken care by images. If there is a change, if there is a bug which you want to fix, if there is a feature you want to add, you need to update your image. So you need to change images. This is one of the top priority tasks in containerization, building images. Once image is built, what we do? We take them and we run them in read-write mode, right? We unpack them. Unpacking an image is called creating a containers. So we create containers using images. Now what we want? We are talking about microservices. We are not going to run everything in a single container. We are having a front-end container, a back-end container, and a database. Now we want these containers to talk to each other. How they will be able to talk to each other? We cannot use a physical network. Otherwise, our IPs will be exhausted. So what we do? We create hypothetical virtual networks inside our operating system. And that is being taken care by Docker networks. So network means a hypothetical network over which your containers are communicating with each other. Because in microservices, there are maybe 20 containers, 30 containers, 100 containers, which are making your entire application. Now we want these containers to talk to each other so that the entire application can work. And for that, they need to talk to each other. How they talk? They talk using virtual networks. And those are container networks. Lastly, the most important things which are related to our storage. Containers are ephemeral in nature, which means they cannot store data. Now, if they cannot store data and someone have deleted my container, my data is gone, which means I am gone. So how to mitigate that? In order to mitigate your data deletion, what we do, we use persistent storage. And that persistent storage capabilities are provided by volumes. We create a volume which is independent object. We associate that volume with our container. Container is created using image and containers are communicating using networks. So these four objects in Docker plays a pivotal role for your entire containerized applications. Image, read-only template, containers, read-write template, networks via which containers talk to each other, volumes for storing your data persistently. So persistent data is stored using volumes. Anything happen to my container? I don't care. My data is stored in a separate object. I will create a new container and I will attach that volume to it. My data is restored. So this is how the entire ecosystem of Docker works. Image, container, networks, and volumes. Lastly, now features. Now, first feature is speed. If I if I take my own example, when I started initially with Unix, it used to take days for me to build one server. When I moved to virtualization, it used to take minutes for me to build one VM. With containers, fraction of seconds will be up and running. Fraction of seconds. This is how speedy they are. So you can create thousands of containers within seconds. Another thing is portability. Now let's say I'm using a data center and I have containerized my applications. My containers are running locally in my data center. Now my organization roadmap is changing and they suddenly start migrating their workload from local data center to, let's say, one of the clouds. I need not to worry. The lifting and shifting will be pretty easy. It's not like doing data center to cloud migrations, which itself is a painful and very critical task. If you have containerized your applications, it will be easier for you to do the same thing on any platform. So the portability will going to be very, very easy. Obviously, there will be certain challenges as per the cloud which you will going to choose, but those complexity will be at least 90% lesser than any other migrations we did in the past. Lastly, the cost optimization. Now you can imagine a server which is having, let's say, 16 GB RAM and 8 core CPUs and let's say 200 GB of hard drive. In the past, only fraction of the resource utilization was there. Now on the same server, you can put your 10, 15 or 20 applications in the form of containers, which means you need not to invest on 10 or 15 physical servers or VMs. On a single server, you can host your applications. So it will significantly reduce your infrastructure cost. There are many other advantages. The downtime reduced to almost negligible when it comes to Docker, and it will be zero downtime when you are using Kubernetes. So there are many other advantages, but these three are the most commonly used and discussed when you are planning to have the cloud native ecosystem in your organization. Lastly, there is another thing which is called registry. Now, what is registry? Registry is a centralized place where we store our images. Now, there are two types of registries, public registry and a private registry. Public registry, anyone can download the images from there. Example, Docker Hub, one of the largest publicly available registry from Docker. Similarly, you have a private registries. Now, I am creating a containerized application, but that's a licensed one, and I'm not selling it free of cost. So it means I cannot upload those images in public registries. So for that, what you can opt private registries. There are open source solutions available, example Harbor. There are proprietary solutions available, example Quay from Red Hat. Even there are SaaS-based platforms available, ECR, ACR, GCR. So ECR, Elastic Container Registry from Amazon Cloud. You have Azure Container Registry from Microsoft Azure. You can have Google Container Registry from Google Cloud Platform as well. And likewise, there are many other solutions available. GitLab provides that. Nexus provides that. So there are many. In fact, GitHub is also providing their own image registries now. But this is something which you need to decide basis on what type of product you are developing. It is open source, put it on Docker Hub. It is proprietary, you need to choose one private registry where you store your organization images. But this is something which is required. You should have a registry in place. So objects and one registry. This is the bare minimum thing which we need to get started with containerization or Docker, right? Before we jump into the practicals, one last thing. So there is something called image build. Now, in order to build images, you need to understand the process of developing or creating Docker files. So what is a Docker file? Docker file is a plain text file where there are only two things. One thing is called Docker defined instructions. Docker defined instructions. You will see certain keywords here. Example, from, run, cmd, expose, entry point, work dir, shell, and so on and so forth. There are total 17 instructions as of now. So these are the things which you cannot change. And that's the reason we say these are Docker defined instructions. Every instruction is having its specific function to perform. So we need to understand them. Basis on that, we need to write human defined or user defined arguments. Which base image you want to use. Example, I'm using Ubuntu 22.04. This is against from. What I want to do on top of it, I want to update it. Which command I want to run, which network port I want to expose, what should be my working directory, and so on and so forth. So for every Docker defined instruction, there will be user defined arguments. What you want to do? I want to take an operating system. I want to update that image. I want to install one package on top of it. I want to create one user. I want to create one working directory. I want to change the specifications or permissions of that working directory. I want to expose my container or application on XXX port. And then I want to start my application with this command. So I want to pack all these things. This entire part will be packed inside one read-only template. And that read-only template is called Docker image or container image or image. And then you give this image to anyone, Mr. A, Mr. B, or Mr. C. They will run it. They are going to get the same application in the form of container up and running. Building Dockerfile, you need to practice it. It will not going to come in 1 hour or 2 hours. You need to practice. You need to containerize multiple applications to get familiar with Docker files. But good part is you need not to remember these instructions. How to get them? I'll show you. You need not to remember them. It's impossible unless and until you work for 6 months or 1 year only in building Docker files. Sorry. Now, how Dockerfile looks. See, so we are actually containerizing one Apache server here, Apache application here. So we are using Rocky Linux. We are updating this image, installing Apache application, which is HTTPD. Then we are customizing index.html, the home page, exposing it on port number 80, and then we are starting. This will be the last command which your container will execute when it starts. So this is the process which starts when your container is coming up. So always remember, majority of the Docker files, you will see cmd as a last command because this is something which will going to start your application. So container will come up with this particular process, which is your application startup process. This is how we containerize our applications. Super. Before we jump into the demo of this entire whatever we discussed, it's always good to explore the docs.docker.com. Now, this is the documentation which you should refer and which you should refer always. Now here, if you come, just give me 1 second, you will see something called reference. If you click on this reference, you should be able to see Docker file reference. If you click here, you need not to remember any instruction. You will get all instructions here. See this. Add argument, cmd, copy, entry point, env, expose, from, health check, label, maintainer, on build, run, shell, stop signal, user, volume, and work dir. Example, I want to see what run does. So just click on it and it will going to take you to this instruction. It will execute the commands to create a new layer in your image. Similarly, if you go up, you want to see something related to copy. So click It will tell you. Copy has two forms. The later form is required for path containing the white spaces. So you will see what it does. It copy the thing. See here. This instruction copy files or directories from source to your image. So you will be able to see the entire details here. And it's always recommended to, when you are initially starting, it's always good to refer this documentation. And even we are going to refer this documentation when I'm going to install a Docker. Likewise, if you go to this manuals, you're going to see the entire details here. Example, you want to explore Docker engine. So click here, you should be able to see everything. How to install, how storage works, how networking works, container, CLI, daemon, manage resources, logs, metrics, everything. So you should refer this documentation regularly and they keep changing it, right? So you will always see updated information here. Super. Now we are going to do our hands dirty with multiple demos. When we talk about Docker, Docker can be installed in two different ways. One, on your laptop. So I'm just writing Docker setup. So you can install Docker on your laptop. This offering is called Docker Desktop. Either it is Linux or Mac or Windows, doesn't matter. Docker Desktop supports all these three flavors. But we cannot run applications in our laptop in production. So what we do, we install it on server. So when you're installing it on a server, Docker become Docker engine. Sometimes people get confused. What is Docker engine? Docker engine is Docker only, don't worry. It's Docker. This is something which we installed on server. Various operating systems, Ubuntu, RHEL, Kali Linux or Rocky Linux or CentOS or Ubuntu, whatever. Multiple operating systems are supported. We will going to install this. I'm going to do everything from scratch in front of you. So let's come back. So first thing is we need to set up Docker. Docker desktop is already on my laptop. So I'm not going to show you that because it's pretty simple. So let's see how we can install it in the real production. So what I'm going to do is I'm actually going to create one server. So let me go to my cloud account and create one server. You can have this server anywhere. Let me put the MFA. And here we go. So we are not having any server running here. Let's see. See here, even if I check, there are many stopped servers. So let us create a new server here. So I'm just giving it a name called demo Docker. I'm taking Ubuntu. You can take any flavor 24.04. I am taking 1 core CPU, 1 GB RAM is enough. But for the application I am going to use, I'm just using T2 medium or T3 medium, whatever you like, 2 core CPUs and 4 GB RAM. I am having my key pair Yogesh Mac test. For the time being, I am using a security group which is having access to all ports so that you can also access the applications. Changing the root disk to 15 GB and bang. So it will take a temporary IP public IP. Let us wait. It is up. This is the public IP. Let me take it. Come back. Come back to my terminal. Let me make it large. My key. Sorry. And here we go. Let me clear the screen, become a root. If I do uptime, see here, few seconds. It's not even 1 minute. The server is up. Let me change the name. I'm putting Docker demo. So this is my server. Now if I do Docker hyphen version, you will see there is no Docker. Now there are two methods which you will see. Sometimes you will prompt to install Docker from the repositories of the operating systems. Don't do that. This is not a recommended approach. The recommended approach is, let me clear a screen, switch back to the documentation here. So go to the Docker documentation, manuals, Docker engine, and you will see install. Click here, you will see various options: Ubuntu, Debian, RHEL, Fedora, Raspberry Pi, CentOS, SE, SELS, binaries, and even, well, many other ways in which you can do it on multiple operating systems. So I'll use Ubuntu here because we have Ubuntu. So if I come back at etc lsb release, see this. So we are having Ubuntu 24.04. Come back, see this. 24.04 is supported version. So we are safe. Come down. This is our new server. We need not to uninstall anything. Scroll back, see this installation method. First of all, we need to set the repositories. So we will just copy this and we will paste it on our server. This will set the repositories for our Ubuntu to install Docker. Again, basic Linux. And in fact, I forgot to mention that Linux is one of the prerequisites for Docker or for any containerization tool. You should be aware of Linux basics. Running a command, what repository is, how to install a package, how to check logs, how to add files, how to append files, how to write files. Such things are the prerequisites for any containerization tool. Docker, Kubernetes, Argo CD, anything. This is done. Next, what we are going to do is again come back. Next step is install Docker. This command, apt install Docker CE. So we'll take this, come back, enter. Yes, that's it. In few seconds, Docker will be up and running for us. All done. Let me clear a screen. Docker version 28.0.4 Docker version is installed. Systemctl status Docker. See this, Docker is active, up and running since 19 seconds. Now time comes to prove. We understood Docker is a client server based software, or it's having client server based architecture. Let's prove it. Docker version. See this, client. This is client details. Server. This is server details. This is open source. We are able to see community edition. So this is server component and this is client component. Even you can do Docker system info and enter. You will see the entire details about your host. And this will also show you you're having client details and then you are having server details. This command is very, very useful because this will tell you what is your registry, how many containers are running, how many images do you have in your Docker host. All those details will be here. Even it will going to tell you which C group version you are using. Even if you scroll down, you should be able to see the root directory for Docker, where lib Docker. Whatever we are going to do in Docker, it will going to get stored in this home directory, which means this becomes a critical directory for us whenever we are doing any maintenance on this server. So take a regular backup of this. If you are doing any changes, upgrades, or whatsoever, make sure you are having where lib Docker backed up. Even as a best practice, your where lib Docker should be a separate file system on a separate VG as well, separate volume group, so that it should not interrupt your root file system and the performance should not get degraded. This is one of the best practices if you are just relying and using Docker. Perfect. Next, before jumping into containers, images, another thing which we should know, and that is called registry. So let's go to hub.docker.com. Now, this is the place where you are going to see the images, publicly available images. And there are four type of images: community image, verified publisher image, user image, and open source sponsored images. So choosing a right image plays a pivotal role in securing your environment. Never rely upon something called user images. Example, if I come here and I search for Ubuntu, you will see this certificate there, which means this is official image. You can use it, no problem. It is completely safe. Sometimes you will see this tick mark. This tick mark means it's verified publisher image. Again, safe. You need not to worry. No malware will going to get injected in your system. Take it. Similarly, if you scroll down and go to some other pages, and you will see this circle. These are called sponsored OSS images. So Docker support the open source projects and supports them in building the images, making them secure, keeping them updated, and so on and so forth. So you can even use them, no problem. But certain times you will see images like, let's say I'll write Thinknyx. So you will see images like this. Nothing is there. 5 years ago, this have been created. An year ago, again, some will be 9 months ago, some will be 6 years ago, some will be 2 years ago. But if you see here, you will not going to see anything related to any tag here, which means these are user images. Never ever use user images in production because we don't know either that user is keeping this image updated, number one. Number two, we don't know either that user is a hacker. Number three, we don't know either any malware or any attack software is a part of this image. We install it and our entire system get hacked. So never ever rely upon user images. Always prefer official images, verified publisher images, or sponsored OSS images. Right? Example, I'll write Apache or HTTPD in simple terms. See this. HTTPD, official image. If I click here, you will going to get the entire details about this. Who maintains it, where to get a help from, what are different versions or tags, quick references, small write-up, how to use this image. So you are going to get the entire reference here. Now question comes, how to take this image? We will again come back. If we do Docker image ls, there is no image available locally on my system. And until it is not available, I cannot use it. Now question comes, how can I be able to pull the image? Very simple. Docker image pull. That image should exist. So if you go back, example, I want to use this HTTPD image and I want it from Docker Hub. So I need not to write hub.docker.com slash something slash something. No. If you are not putting anything, Docker will automatically assume you are talking about Docker Hub. But if you are having private registries, you need to put, let's say, abc.com. This is my registry slash my project name, let's say web app slash whatever image, let's say httpd colon which version, let's say v1. This is the complete naming convention of an image. This is registry name. This is repository name or project name. This is image name. And this is image tag, which is version. But in case if you are taking anything from Docker Hub, you need not to write all this. You just need to write the name of the image. Example, httpd. And let's say I want a latest image. Although in production, you should not use latest because latest is latest today. But after 5, 6, 7, 8 months, latest be something else. So it might create conflictions. Always better to use a specific tag or a version. If I enter it, what will happen? The image will be downloaded. Done. Closely see this. I wrote httpd colon latest. Docker have automatically resolved it to docker.io, which is hub.docker.com. Under it slash library, which is the repository name. Under this httpd, which is the image name, and latest is the tag. Sorry. Image downloaded. Docker image ls. See here. My image is here now. If my image is here, I can create a container out of it. And I want to access this container to see if everything works or not. Now what I'm going to do is I'm going to use this image and create a container out of it. Docker container ls. There is no container at present point in time. Let's create a container. Docker container run is the command. Interactive terminal demonized mode. I want these three things. I want to give it a name. Let's say web app. I want this container to be accessed from outside as a public web server. So I want to give it a port. HTTPD works on port number 80. This is my host port where I want to access it. And this is my container port. So my image is having port number 80 exposed and I want to access it on the same port of my server as well. If you want a different one, you can give different one. Example, I want my server port to be used as 3000. So I can access this container on 3000 publicly, which will going to route the request to port number 80 of this particular container. Once done, I need to give the image name. That's it. Now you will see how quick the container will be created. 1, 2, 3. Container is up and running, all done. If I do Docker container ls, see here. Let me make it a little small to show you. See this. This is my container ID, short container ID, 12 characters, long container ID, 64 characters. This is the image. This is the CMD, last command which my container executed. Metadata created 5 seconds ago, container came up 4 seconds ago. And this is exposed on IPv4 and IPv6 both on port number 3000 of a server, which is redirecting traffic to container at port number 80. Name of the container is web app. Let's take the public IP now. Now this is my public IP of a server. During the creation time, I have given all ports which are open. So take this, come here, port number 3000, enter. If everything is okay, you should be able to see the details here. See this, it works. My container is responding with it works, which means my container's index.html page, home page is having it works. All done. Wow. Go back. Let me clear a screen. Docker container ls. You can do multiple things with it. You can stop this container, you can start this container, you can uh, log in inside this container. You can do multiple things. Example, Docker container stop web app. Container is stopped. If I do Docker container ls, it is no more here. If you want to see the stopped containers, just do ls-a. A means all. See this? It is exited 8 seconds ago. I want to start it again. Docker container start, and I'll give web app. Super. ls up and running now. Created 2 minutes ago, up from 3 seconds. I want to go inside this container just to check things. Docker container exec -it. IT means interactive terminal. Come sh or bin bash. See this. I'm inside a container now. This is my container ID. 8fe something. See this. So I'm inside a container. Want to come out of it? Exit. Done. Run Docker container ls. Your container should be up and running. Perfect. Now, how to create our own image. Let's quickly see that. Now, what I'll do is let me create where temp, let's say my app, and go inside it. You can use Python, you can use Go, you can use Node.js, whatever. But I'm going to use a simple example here, which is web app, this Apache one, so that you can relate it with the previous example as well. Now, what I'm going to do is I'm going to create my own image, which should show my own result or my own homepage. So I'll create vi Dockerfile, capital D, all small case. You can give any name, but this is the standard practice so that you can identify which is your Docker file in your application folder. Now, from. From means which base image, which OS image you want to use. So let's come back and let's see. Let me use Rocky Linux. This one, official image. Let me click and I'll use a tag 9. Come back, Rocky Linux 9. I want to update this image. yum-y update. Important point. Your Docker file should be non-interactive. It should not prompt. If it prompts, it will fail. Hence, that's the reason I'm giving -y. Next, I want to install Apache application. Now, next, I want to copy. I want to copy my index.html. So I'll say index.html. I need to create this file now and put my data. So I'm saying my current working directory is having index.html. Take that file and put it in where www.html index.html. This is the file for your HTTPD. This is application file. Next, I want my 80 port to be exposed. And finally, I want my application to get started with the command httpd hyphen d foreground. So httpd hyphen d foreground. You can give a space here, or if you don't want to give a space here, you can remove also. Now, the only thing pending is index.html file. So I need to create this file as well. Rest all of the steps are okay. So I'll save this cat Docker file. So this is my Docker file. I'm saying current working directory should have index.html, which is not there. So I'll create index.html file. So I'll say header start. This is the magic of Docker, and I am closing it. Done. So if I do ls, I'm having index.html in the current working directory, which I have given a path here. So this file, which is this one, will be copied to this file in my image. And this is my Docker file, which we have created. Now, if I do Docker image ls, I'm just having one image, which is httpd. I'm not having Rocky Linux, and I'm not having whatever image I want to create. Let's create it. Docker image build -t means tag. So I'm creating an image called myapp:v1. Myapp is a name, v1 is a version. And then I'm giving the path of the directory where my Docker file is present, which is current working directory. So I'm giving a dot where the directory where my Docker file is present. Enter. If everything is okay, see here the build is started. So it will automatically going to see here all steps you will see. It will automatically download the Rocky Linux image. It is updating the packages in that. You will see all steps here. How much time it took, you will see all details here. See here 191 packages are getting updated. Sorry. Now third step started. Yum-y install httpd. Done. Image is ready. See this. If we do Docker image ls, see this. 11 seconds ago, my image got created. It's time to test this image. Docker container run itd -name, let's say test container -p, let's say 4000, port number 80 where my container run, and then my image. My image name is myapp:v1. Enter. If everything is okay, we should be able to see our container up and running. See this. Testcon. Up and running since last 6 seconds. Accessible publicly on host port, which is 4000. Let's check that. Come back, take the IP, same, change the port to 4000. If everything is okay, then we will see the magic of Docker. So this is the magic of Docker. See here, my own image is built, my container is tested, and now I can publish it and I can use it. This is okay. Now, let us see one live application in action. Although we could have many applications which we can use, but this one is the most simple with various microservices. So we are going to use something called voting app. This application consists of multiple language stacks. So the first is Python. This will going to be a front end where you can give a vote. First container. Then this vote will going to get registered in the cache. So we are going to have a Redis. Then there will be a framework which is written in .NET Core. This is checking if there is anything in the cache, taking it, processing it, and putting it in a database. This DB is Postgres, and this is called worker container. So we are having Python, Redis, .NET Core, Postgres, and then there will be another front end which is written in Node. This front end will read the database and show the result to the user. So this is vote container. This is result container. This is DB. This is worker container. And this is Redis cache. If these containers can talk to each other, then only this application will work, which consists of 5 microservices. Now, what we need to do first? In order to get it worked, we need to create one hypothetical user-defined network. First thing, so that these containers can talk to each other. So we are going to create a user-defined network. This will going to be the first step. Second step will be we need to download the images. You can build it from the source code, but that's already built. So I'm going to download them from my Docker Hub account. Once this is done, we will create the containers in this network. And then finally, we will test our application. If there are issues, we will troubleshoot it together. These are the typical 5 steps we do whenever we containerize any application. Let's do it now. Come back. I'll switch back to Docker Hub first, and I'll not here. I need to write here. See here. So I have vote, result, worker, DB, and Redis. Um, these are the images. And if you see, they are very old, which means I'm using this example many a times. So I built it 6 years ago. Let's see if they work. Come back, clear the screen. Now what we will do is we will create a network first. If I do Docker network ls, these are the 3 networks which comes by default. Null network, host network, and bridge network. By default, Docker is using this bridge network. But the problem is in this bridge network, the DNS is disabled. So we should not rely upon this bridge network. We should always create our own bridge network, which will be having DNS enabled automatically. Let's do it. Docker network create. Just do -help if you're new to it so that you can get the options as well. Docker network create. If you see this driver, this should be bridge. Even if you're not giving it, the by default one is also bridge. But just to show you, I'm just giving it a bridge one. Then you can give a subnet as well in case you want. So if you see here, there should be something called subnet. Otherwise, Docker will automatically take by default subnet, and it should be 172.17 or 18.x.x/16. We will take a smaller one, let's say 192.168.10.0/24. So we will take little small subnet, and then you can give a name. Let's say I'm giving appnet. So my network named appnet will be created of type bridge with this subnet. So if I do enter, done. Docker network ls, you should be able to see your appnet. First part is done. Second part, images. Docker image ls. I need to download the images, right? So again, step number 1, done. Step number 2, we are doing it now. Come back, Docker image pull. Come here. So we have Thinknyx vote. I think there should be V2 version of it, which is the updated one. Let me check the tags. Yeah, V2. So I'll take this and I'll take V2 version. So I'll switch back, V2. Image is downloaded. Likewise, we will take Redis, confirm it. So we are having Redis, DB, worker. They all are V1. So Redis, worker, worker one is little big image because it's .NET Core based. So it will take probably 60, 70 seconds. Super, done. Next is DB. Super. And the last one is the result one. Result one is also having V2. Let me cross verify it. Yeah, V2. So come back, V2, result. Bang on. Docker image ls. See, these images are here now. Now, second step is done. This is completed. We need to create containers now. This container is public facing. This container is public facing. So we need to expose them. All other containers are internal containers. So we will not expose them. Come back. So Docker network ls. So we have created appnet. Let's create our first container. Docker container run itd hyphen name. I'm giving it a name called vote hyphen p. Let's access it on port number 81. This has been created on port number 80. Now we need to give hyphen net, the network where we want this container to be created, which is appnet. And then finally we will give vote v2, enter, created. Docker container ls. See here, container is up and running, which means things are working fine so far. Second container, Docker container run itd hyphen name. We will give it a name called Redis hyphen net appnet. You can give space or you can give equal to, both will work. Example, I have given a space here. So if you can give equal to, that will also work. We don't want this container to be exposed outside. We want it to be internal container. So we are not going to use the port publish uh, option here. So it will be internal container. And then we are going to use Redis colon v1. Similarly, we will use other. So let's create a DB first. Name DB, appnet. This is the DB v1. Let's create a worker. Let's change the name as well to worker. Enter. And lastly, the last one, which is our Node.js. Again, a front end. So Docker run itd hyphen name. We will give it a name called result. We will give hyphen net as appnet hyphen p. We want it to be exposed on port number 82. The container port is port number 80. Come back and take the result image colon v2. So appnet name, super, done. Docker container ls. If I make it little small for you to check, see here, 1, 2, 3, 4, 5. Vote, Redis, DB, worker, and result. And they all are up and running. All 5 containers are up and running, which means things looks good. Let's test them. Copy this IP, come back, port number 81. See here, a front end. And again a front end, but for result. See this, no votes yet. So if I come here, let me give a thumbs up. See this, my vote got registered in Redis. Worker have taken it, sent it to the database, and my result should read it. See here. If I want to change my vote, change, come back, see this on the fly. Again, I want to change, come back, see it on the fly. This is how various microservices are talking to each other and things are working all together in containerized world. So if you go to Udemy, you should be able to see few of my courses. Let me check for Docker. This one.